that there's still some very active radio amateur groups around, and but also concerned that this electromagnetic emissions is becoming a problem, and in fact I think it's going to be more of a problem for you guys in future. So just as an overview of the talk, I'll say a little bit about my background and the research that we're doing at Macquarie Uni in this area of power electronics and power systems. I'll even talk a bit about electric vehicles and things, because this is part of what's driving the transition in energy systems that's happening. And power electronics are a large part of that, and this is the source of a lot of these emissions that that are becoming noticeable. Particularly, I'll mention some stuff to do with converters and inverters, the sort of thing that you connect to your photovoltaic panels. And lead lighting is another particular problem that I was talking with someone about previously. I'll review some of the standards around this, but the standards are really, I think, as good as the paper they're printed on to some extent, and really we need to talk about EMI mitigation techniques. So that's the path we'll take. All right, so I'm an electrical engineer originally. I was a trainee with AWA back in the 1970s and 80s, and was basically a telecommunications, electronics type of engineer. I worked with AWA for a couple of years after graduating, and then went and did a PhD in medical imaging. I was part of a small group that built an NMR imaging system when I was at Sydney Uni. And actually I'm sort of jumping ahead of myself a little bit. I became an academic at Sydney Uni, and then in 2002 moved to Macquarie to start up the engineering program there. And there's a list of all the sorts of different things that I've worked in. I'm probably a bit of, in an academic sense, a jack of all trades, and some would say a master of none, although I beg to differ. I used to be an amateur radio person myself. Was my call sign, although I haven't paid my licence fees for over a decade, so I'm well and truly lapsed, I'm afraid. As I said, I started out as a radio trades apprentice and engineering trainee with AWA. I even worked on Interscan, you might remember, and on first generation optical fibres, which they were doing research in. I was actually at the North Ryde facility, the engineering products facility. So I did my undergrad at the University of, well, it was New South Wales Institute of Technology then, and my project was on antenna measurements, and that was done at CSIRO Radio Physics. As I mentioned, we built a small NMR imaging system as part of my PhD, and 1.5 Tesla, which was common magnet strength back then, gave a resonance frequency for protons, which is normally what is most commonly imaged, at 64 megahertz, which was, that time was right next to channel 2 of the TV station. I then became an academic engineer and did most of my research on optical fibre lasers and guided wave devices for telecommunications and sensing. This is sort of when the telecommunications superhighway was taking off. And then, as I said, I moved to Macquarie University. For the last 5 years, though, I've really been moving back into more electrical stuff with sustainable energy systems, and working on power electronics, smart grids, electric vehicles, a little bit of solar thermal and waste to energy conversion as well, because I see this as really the big problem for society going forwards. We're going to have to transform our energy infrastructure over the next couple of decades. Okay, so one of the projects we're working on is what we call integrated energy conversion. The original goal of this project was to try and put a power converter on a chip. In fact, Macquarie University is famous for putting Wi-Fi on a chip. You might recall there was some IP that came out of radio astronomy at the CSIRO for wireless communications that would overcome multipath. That was put onto a chip and commercialised by a couple of professors at Macquarie University before I got there. They'd left by the time I got there, although we're obviously still in contact. But anyway, this project has become more about using gallium nitride devices, which I'll say more about shortly, in power converters such as this. This is a power converter, DC to DC power converter. Computer controlled, there's an FPGA here that's actually controlling the switches on that power converter, and then a number of measuring instruments around that. Yeah, novel circuit topologies, trying to increase the switching frequency, shrink the size of these power converters, and also include some smart control in there. Another project that we've got, this one's sponsored by Optus in fact, is about managing the impact of electric vehicles on the power distribution grid. And to manage the impact you have to know where they are, so part of this project is about monitoring them. This is a project a student built to go into a vehicle to do the tracking and communication of things like state of charge of the battery and so on back to a central server. And the idea is we're going to log a lot of vehicles, collect the data and work out how to manage them optimally. So that's sort of a smart grid type project. Now, oh dear, I don't know if, this thing has started to go a bit funny on us. Can we start this one up again?
Oh, I reckon a few minutes.
Yes. What's going on here? I looked at it earlier today and it was fine. Maybe we'll try the PowerPoint,
Yep,
Richard. How do we close this one down? Right. Okay, try again. Well, I'll try starting this up once more. Yeah, it's back. All right. Let's keep our fingers crossed.
That's not controlling the electronic car driving.
Whoops.
Windows operating system in the car.
Okay, and what was it? F5 does that? Yeah. Okay, so that's where we were. Right. So, so before I get on to electromagnetic emissions, I need to explain sort of what's happening behind the scenes, and basically, power, or I prefer to call it energy technology, is moving from what we have essentially now to a much more distributed system. And I give the analogy here that what's happening in power systems or energy systems is sort of following what happened in telecommunication systems just a couple of decades behind. So if you remember, those of us who can remember 2 or 3 decades ago, there used to be a TV and a radio transmitter on the hill, and everyone had a little receiver, so there was one source and many receivers, and there was no communication between the receivers or the consumers. Now we have the internet. Everyone is a source or a sink of information, and everyone is connected to everyone else. And energy is likely to go the same way. So everyone will have photovoltaics on their roofs, or a fuel cell out the back, and certainly batteries probably in the garage. And they may be sharing their energy with other people who need it more than they do. There will still be grid connections, probably, because that sort of backup and guaranteed supply of energy is necessary. And in any case, we need the distribution grid to share the energy. So, but it's going to be that everyone is going to be probably a lot more responsible for their own energy consumption and use. And the only way to make this happen is by having telecommunications in parallel with the energy system, monitoring and controlling it and optimize. So in theory, if this is done well, you can optimally use the energy system and avoid, things that we've been hearing about lately, such as overbuilding on the transmission and distribution systems, which have pushed our electricity prices up by about a factor of 2 over the last 5 to 10 years. So at the moment, we've got a lot of safety margin on our power system in order to cope with 1 or 2 hot days a year when everyone turns their air conditioning on. With an intelligent system, we can avoid so much investment in infrastructure, although we'll be running a little bit closer to the edge. But if everyone has some control over their energy consumption and generation, then hopefully things will work well. So these are some of the characteristics of such a system. And one thing that's not mentioned there is that power electronics is going to be central to making this work as well as the telecommunications infrastructure. One of the things that, the other thing that we've been waiting for this picture to be realised is for battery or storage costs to drop. And this is in fact happening fairly rapidly now. So just as we saw photovoltaic panels, the cost of those drop rapidly in the space of a few years ago, the same thing is now happening in battery technology. And someone's coined a Moore's law, if you like, of battery storage systems. You're probably aware the Moore's law was actually first proposed for increasing density of devices on integrated circuits. And we're seeing a doubling every year or two of the density of devices. Well, we're seeing which had an impact on the cost as well. Well, now we're seeing an exponential drop in the cost of battery storage, driven partly by the increase in scale. You would have heard of Tesla and their battery factory and so on.
So which batteries are you talking about here? Because
lithium-ion batteries.
Yeah, so
Yeah.
My car batteries certainly haven't been increasing like that.
No. This is specifically lithium-ion batteries that go on your laptop or go in your electric vehicle. The lithium-ion, it looks like it's going to be the technology of choice, partly because of cost, but energy density is what drives it. You can get, there are a lot of other battery technologies that might be suitable for home storage, but not for electric vehicles. And the fact you can see drones flying around now is because of the energy density in these lithium-ion batteries. Lithium-ion is still developing. There are various versions of that coming through, but in any case, the general thing is this drop in cost, and it's not just the battery itself, it's the installation costs and everything around it. So battery systems are reducing, so people can now afford the electric vehicles and afford to have battery storage in their homes to store the excess photovoltaic energy that they generate during the day, which currently, or very soon, they won't get any money back from the distributor for putting back onto the grid. So this synergy between storage and renewable energy is really what's going to enable a smart grid, or what we're starting to coin the Internet of Energy. It's going to enable that in future. The impact on costs. So this is our standard electricity costs coming from the central generation system, going up over time. This is the rapid decrease that we've seen in the cost of electricity generated by photovoltaics. That's already dropped below the cost of electricity that you buy off the grid. However, it's not much use if it's not there at night time when you need it. So that's where this line is for batteries, and the cost of batteries is dropping. And at some point, we're predicting the combined cost will drop below the cost of electricity off the grid, which is going to force electricity generators and distributors to find other ways to provide energy and lower their costs as well. So I won't need to talk about that one on the right. So electric vehicles. So this picture was from a year ago, and they just calculated that at that time they'd passed 1 million in sales of electric vehicles at that date. And the number of vehicles being sold is increasing, and it's starting to go up exponentially, a bit like the photovoltaics did. Mainly overseas, I've got to add. Still not seeing much traction here, but just as a point of interest, one report that was published a few years ago said that, or predicted, that by 2020, 20% of new vehicles sold will be electric. So that's how I remember it, the 2020-20. And 20% of new vehicles being sold a year is a significant number. So we can expect to see electrification of transport generally, but particularly these sorts of vehicles happening over the next decade or so. Again, the cost of electric vehicles is quite high to purchase, but the cost of running them is quite low. So the lifetime of the vehicle, actually some of them are cheaper than an internal combustion engine vehicle if you do the calculations. Here's a slide showing the uptake of electric vehicles in New South Wales. So this is a very local figure. Surprisingly, Tesla's rising rapidly despite the very high cost, and all brands are also starting to rise relatively rapidly. The really telling graph for me is this one. Now, this is not for Australia, this is for the US, but it's a graph of what they call alternative fueling stations. So one of the problems with electric vehicles, if you can't go out and charge them anywhere, there's no point in having one. Or if you've got a hydrogen powered vehicle or any other powered vehicle, you need the infrastructure in order to fuel it. So hydrogen is one of the very small bands on this graph. Liquefied natural gas is the blue one. Not sure where that one is actually. Propane is this light blue one here. But the orange bands are the electric charging stations. So you can see since about 2011, the last few years, the number of charging stations in America for electric vehicles has just been taking off. And certainly in some parts of America, electric vehicles are becoming very, very common. California is probably one of the more progressive states in that respect. So the cost of vehicles will start to drop. The cost of storage will start to drop because all of these electric vehicles will use their batteries for a few years, several years, and then they'll need to be replaced, but they'll still be perfectly good for home storage applications and things like that. So there'll be a significant market in second-use batteries, and the whole economy will start to feed off itself and grow. So that's what's behind developments in power systems. Now I get on to power electronics, and please be patient, I'll get on to electromagnetic emissions fairly shortly. What I want to start though with power electronics is what's driving the changes that are going to fuel enable the changes in power systems. So silicon devices, which are of course the most common and developed technology, have if they're used in power converters, have limited bandwidth and limited power capability, and generally of course the bigger you make them, the lower the bandwidth, because the frequency that they can switch at scales inversely with their size. The last few years we've seen gallium nitride becoming very interesting for applications in power conversion. Silicon carbide's always been there for quite a bit longer, and both of these technologies can go into higher frequencies and or higher power ratings than silicon, and they can also go to higher temperature. So this spider graph comparing the three different technologies, silicon is this little circle in the middle, gallium nitride's the red one here, and silicon carbide's this one. So silicon carbide wins if you want to operate at high temperatures or have high thermal conductivity to get heat out. Gallium nitride works best in terms of breakdown voltage, so compactness of device for a given operating voltage, but otherwise they're both well ahead of silicon. Now silicon carbide's quite expensive because of the way it's produced. Gallium nitride used to be quite expensive. In fact the gallium nitride technology has come out of a little bit the gallium arsenide technology, which is, if you go back to your mobile phones, the power amplifier in your mobile phone is probably a gallium arsenide transistor because of the high power density that gallium arsenide can manage compared to silicon as well, and at the high frequencies. The thing that's been enabling the gallium nitride, coincidentally, is its use in light-emitting diodes. So previously gallium nitride was grown on silicon carbide, so the cost of the combination was high, but they've worked out how to grow gallium nitride on silicon wafers, which reduces the cost significantly, and so now it's sort of getting into the domain of being a commercially attractive device to use in power electronics as well as lighting, which was the original driver. So the materials have led to new devices, and that's leading to new circuits with higher operating frequencies, higher power capabilities. So I'll give you some sort of cutting edge numbers. These are measured numbers. I'm not sure how they measured them, so don't press me on that, but these devices can switch very, very fast. 600 volts in 2 nanoseconds is 300 kilovolts per microsecond. If you put that voltage across a 10 picofarad capacitor, you would get 3 amps. 2 amps at 2 nanoseconds is 100 kiloamps per microsecond, and if you put that current ramp across a 1 nanohenry inductor, which I think is a millimetre or 2 of wire, you get 100 volts. So there are challenges in using these devices if you want to access this really large bandwidth. The thing is that because of the fast switching, you minimise the time between when the device is off and on, and this reduces the switching losses. So you can go up in frequency and still maintain good efficiency in the power converter. But you do have other challenges to deal with, which is that you've got to make sure the circuits are broadband and minimise the inductance where it's a problem, or the capacitance. So more efficient switching, but again, these rapid changes really give you broadband emissions. Just to illustrate the impact of these increasing switching frequencies going from 72 kilohertz on the left to a megahertz on the right, I'm pretty sure these are circuits used for electric vehicle charging or designed as electric vehicle chargers. You can see the reduction in volume or the increase in power density that comes from going up in frequency. So all of these converters, of course, will have the potential to produce interference in all the amateur radio bands. But the lower you start, I guess, the more interference you'll have. Here's another slide showing that, again, going from bulk devices down to hybrids, down to even integrated circuit level. As you go up in frequency, you can shrink the size of these converters more effectively. This particular board here, you can see it's the size of a small US coin. In case you can't read it, the efficiency, it's a buck converter, so I think this one, it drops voltage in from 48 volts to 12 volts out. Switching frequency of a few hundred kilohertz. The efficiency here is over 97.5%, and that's at 10 amps in something not much larger than a small coin. So the power densities are really getting quite extraordinary. There are, of course, again, challenges that come with this. As the thing shrinks, the efficiency has to go up because the same amount of even a smaller amount of heat being dissipated in a smaller volume gives the same sort of thermal flux and temperature drops, and there are limits, of course, that you have to stay within in terms of the temperature of the active devices. So everything's shrinking, and it's an interesting time because some of these challenges are quite fun to deal with. Okay, another example. This is an example of commercial LED drivers. This is an older one, below about 80% efficiency, less than 5 watts per cubic inch, switching between 50 and 100 kilohertz. And then a more modern device. This was published a couple of years ago at the Power Electronics conference. 93% efficiency, switching at a few megahertz with 10 times the power density. But again, lots of emissions from both unless you take care to avoid them. Have any of you heard of the Google Little Box Challenge? No. Okay, so a couple of years ago, Google, together with the IEEE, which is the professional institution for electrical engineers in the US, put up this challenge, and there was $1 million prize to produce a power converter, 2 kilowatts, within this size box. The winner ended up being this company, which I think is based in Belgium. It's a power electronics company based in Belgium, and this is the product they used to have. This is what the challenge expected them to produce. This is a pile of post-it notes, and this is what they actually came up with. So again, huge increases in. They went from they exceeded the requirements by a factor of 3 in terms of power density. The switching frequency varied between 35 and 240 kilohertz. That was optimised depending on the load. Yeah, you can see the extreme reduction in volume there. There was one university group from a university in the US that came a close. Well, actually, they had to drop out of the competition. They were winning. They had the best specs, but unfortunately their converter failed whilst it was under testing. They all had to undergo independent testing, and unfortunately their converter failed. Otherwise they would have won the $1 million. But so this is the specs of that converter. Again, 98.5% efficiency at a couple of kilowatts. So it's the sort of converter that you'd see connected to a photovoltaic installation on a domestic roof, a couple of kilowatts. You probably can't read the specs. That was what Google expected. That's what they produced. This is a thermal image of the converter while it's working. The temperature gets up to about 50 degrees Celsius. And we're starting to get into the things that are probably of interest to you guys. This is the electromagnetic emissions. They had to be obviously within the, in this case, the FCC standard limits for both quasi-peak and average, which they achieved, probably mainly due to the packaging that the converter was in. You can see, I think this is probably the fundamental switching harmonic here, and you can see just how many harmonics of the fundamental switching frequency are produced in the output. This converter was also using gallium nitride devices. Part of the key to getting this compact power converter was the use of widebandgap power devices that are coming onto the market now. Just to bring it a bit closer to home, this is some work that we've done at Macquarie University. This is not a compact converter. It's not even a particularly high voltage or high current one, but it's a relatively novel topology. It has 4 switches in it, which switch the current through a transformer, and then you've got a rectifier and voltage doubler on the output. It is controlled by an FPGA up here, so signals go down to turn these 4 switches on and off to control the conversion. And this is one particular result that we did, measuring the conducted electromagnetic emission coming out the source, the input power leads to the circuit. On the left is what we measured initially, and this goes up to 300 megahertz here. So fundamental switching frequency of 24 kilohertz and 30 megahertz, not 300. 24 kilohertz switching frequency, over 1,000 harmonics in that spectrum coming through. And this is partly the main problem for people in Radio Amateur Society. Is this covers probably most of the bands that you're interested in using for communication, and you can't easily filter out the noise because you'd then be blocking out the whole band. The noise produced by these converters is quite broadband. So how do you reduce these emissions? How do you get around these problems? One approach is to use clever modulation techniques, which we've been working on. And I won't go into the details, but on the left is before and on the right is after, and you can see this peak here is reduced by about 10 dB just by using clever modulation techniques. But beyond that, you really do have to use shielding, proper techniques on the input and the output to eliminate interference from getting out into the outside world. Yep.
Did you have a low-pass filter on the input?
Actually, this is a low-pass filter. Okay, it's called a quasi-Z source inverter because it's got an impedance between the supply and the switches. So these 2 inductors, together with that capacitor, are effectively a low-pass filter. Even if you just go through that capacitor, you've got an inductor in series. The problem is that unless you do it very carefully, these filters will be a low-pass filter only up to a certain frequency. So probably what you can see here is where it is effectively a low-pass filter right down in the lowest few megahertz, and then you've got leakage and other stuff getting through anyway. Maybe with a bit more careful design, we could have reduced the emissions over a broader band, but you'd have to use special techniques for building the inductors and make sure the capacitors were designed to do that as well.
Grant,
Yep.
you know the ACMA reduction that you put in place in it?
Yep.
Wouldn't you have 2 circuits in parallel that in reverse of it, cancel each other? Or?
Yes, what you're sort of talking about there, if I understand correctly, is active noise or active filtering. And it's a fairly commonly used technique at lower frequencies, particularly to reduce harmonics of the power frequency. Often in transformers and other devices you get harmonics being generated which also reduce power quality, and the power people like to keep these off their lines if possible. So you can use active filters at lower frequencies. I haven't seen it being done at these sorts of frequencies, but in principle the digital circuits are powerful enough now that you probably could. It's an interesting thing we could look into. Yep.
What about adding jitter to the switching circuit?
Well, that's effectively what we're doing here actually, a form of jitter to dephase the harmonics. The problem is when you've got a regular switching frequency, all the harmonics add up in phase at certain frequencies, which are of course integral multiples of your fundamental. If you can change the timing of your switching a little bit from cycle to cycle, you dephase all those things, and that's why it really only reduces the peak. It doesn't reduce the average, because the emissions are produced every time one of these switches opens or closes. If you can open or close them less frequently, you will reduce emissions that way as well. So another approach that we've taken to reducing emissions here is to minimise the number of switching operations that you do. But these are all, they don't solve the problem completely. They all help, but they don't solve the problem completely.
The previous slide, the contrast one,
yep.
There was a switching frequency variable. Oh yeah.
Yeah, so...
is that the winning one? Or?
This is the winning one, yes. And you'll see that, the efficiency of these power converters usually drops off at low load. And that's because the power converters consume a certain amount of energy, whether they're actually putting energy through or not. So that's why the efficiency drops off there. But if you change the switching frequency, you can sort of tweak this so that the optimal point of maximum efficiency moves around to where you need it. And I think that's why they've used this quite a wide range here. That's unusually wide to use in a switching. Okay, that brings me on to LEDs. So ACMA's signs up there because they have standards about emissions from all these sorts of devices. But this is off their website. They basically say that, yes, these things have been measured to produce interference out to 300 megahertz. However, they don't actually measure these things themselves, as far as I can gather, before they're imported into the country. They rely on the supplier or the importer to do the tests and provide the evidence that the devices meet the standards. But clearly they're probably not. And so their caveat at the bottom here, it says, if it appears that the globes are the problem, you may consider returning them to the place of purchase or contact the manufacturer directly. Don't call us.
Yeah, that's great. They're your globe, but what if they're your neighbour's globe?
Well, this is actually the problem. There's you've probably seen reports on the web about people's garage doors opening and closing at random, and it's actually triggered by a neighbour turning their lights on and off, or someone has intermittent interference on their TV, and again it's because of a neighbour with their noisy lighting. So if that's the case, and you know a bit about it, you can go around hunting and trying to correlate the interference with where it's coming from and then approach the neighbour. If you don't understand this sort of stuff, good luck. It's sort of like black magic. Here's some measurements that I downloaded off the web. This is the website of some commercially available LED lighting. So compact power converters are very important in this case, of course, because the power converter is in the back of the LED lighting fixture, because this goes into a standard light socket. So they have compact converters in here, but probably very little shielding. And this is off and this is on. This frequency here is about 200 megahertz. So you can see that, again, this particular light bulb, when you turn it on, starts producing quite a lot of interference over a very wide range of frequencies. I don't know, they didn't give details on the website how this was measured. I don't know if this was conducted or radiated or what other form of emission. However, you can see that there are potential problems there over a broad range of frequencies. Here's another one, and this is by a different manufacturer, again compact LED light. Off on the left, on the right, and this has an extraordinary amount of emissions. The difference between on and off here is about 40 dB. So some of these lights are very, very noisy, and you can understand why they will cause problems for not just radio amateurs, but even other systems. And this is becoming a theme. This is an extract from an article in IEEE Spectrum from a few years ago, saying electronic noise is drowning out the Internet of Things. So the Internet of Things is where everything has a smart communication, usually wireless communication device attached to it, so you can monitor things. In the smart grid, you'd be monitoring power consumption in devices like your refrigerator or your air conditioner. and ideally you'd be able to turn them on and off depending on need and the cost of electricity and various other factors. However, all of the power electronics coming out is producing so many emissions that, and it's going to get worse, that it's drowning out the wireless communications needed to run the Internet of Things. So this is potentially a significant problem, not just for you guys, but more generally for smart infrastructure. What do we do about it? Well, I've mentioned the ACMA and the standards. This is a list of the relevant standards that apply in terms of the emissions, maximum emissions they should produce depending on the type of equipment. There's lighting, motors, information technology and so on. This standard governs how to do the measurement. There's no point having these standards on emissions if you're not using the appropriate technique to measure them. But as I've said, these things equipment doesn't seem to be checked unless there's an obvious problem, and then maybe you can send it to someone to check them. These are the actual values in those standards for emissions. We're talking tens of microwatts, dB microvolts here for conducted emissions, or dB microvolts per metre for radiated emissions. So tens of dB microvolts. I guess that means getting close to millivolts. Anyway, I'll leave this presentation for you if you want to, refer to some of these things later on. So, what do you do about electromagnetic emissions? You guys probably know more about this than I do, so I'm treading on thin ice here. All I will say is I used to teach engineering electromagnetics to third-year students when I was at Sydney, and it was one of my favourite units to teach. Wasn't one of the students' favourites, but it's an interest. Electromagnetics I just find fascinating. So if you've got interference, we can define three different forms. There's conducted, where you've either got a common impedance or maybe a waveguide effect happening. There's near field, or what I would call induced interference through either capacitors or inductors, parasitic capacitors and inductors. And then there's far field, which is radiated emissions. And when you look at the impedance of the different types of emissions, in the far field, the impedance is 370 ohms for a plane wave propagating in free space. As you get closer to the source of the emissions, it depends on what type of source it is as to what happens to the impedance. If it's an inductor, it will mainly be producing a magnetic field at the source. So your E over H ratio will be very low and you'll have a low impedance source. If you and that would be, for example, a loop antenna. That's a small inductor. If on the other hand you've got a wire antenna, which is open-ended, this is more like a capacitor, the impedance goes up. And this boundary between near field and far field is a fuzzy boundary, but it is reasonably well defined, and it's this lambda over 2 pi. So I guess you're familiar with that, or if not, this is a nominal boundary at which we say, okay, it's far field if it's further away than that, or it's near field if it's closer than that. And the technique for dealing with the interference depends on where you are, whether it's in the near field or the far field, and the impedance. A lot of EMI mitigation techniques rely on impedance mismatching, actually. So it comes down to that. At 1 megahertz, this boundary between the near field and the far field is about 50 metres. So even at relatively low frequencies, at relatively low frequencies, you're most likely going to be in the near field. When you're getting up to 100 megahertz, that boundary is half a metre. So then it's more likely, certainly if you're at one end of the hall from the other here, and you're getting interference up there from something down here, that's probably radiated, unless it's going through the wiring as a waveguide or something like that. How do you eliminate electromagnetic interference? Well, there's basically three techniques. You can reduce the sensitivity of the receiver, which is the last thing you guys want to do. You can reduce the emissions from the source, which if it's in your neighbour's property, maybe you've got limited control over, or you can try and block the path between the two. There's a few publications here on how to deal with electromagnetic interference that I downloaded off the web that may or may not be useful to you, but I'll go through a couple of these techniques now, which as I said depends on the impedance of the source and the nature of where the interference is coming from. Okay, so common impedance coupling. If you've got a number of circuits driven off a common power line, and there is a impedance in this power line, and it may be an inductor which has a high impedance at high frequencies, or it may just be a resistor, then current through this circuit, for example, will cause a voltage drop across this part of that circuit, which will raise the voltage for these other circuits at the same time. So you can get currents in this circuit causing interference through the power lines on the other circuits connected to that common power path. The way around that is to use a common grounding point for all the circuits, and then assuming that this source is really a low impedance and it's a good earth here, currents through this circuit cannot interfere with the other circuits. So that's how you get around common impedance coupling. This common grounding point is also good because it avoids earth loops, which is another issue. Down here, for example, if you've got an earth loop, then you can have magnetic fields linking with that, causing currents in that, which will also cause difference in voltage at different earthing points, and that's another way for interference to get into circuits. When we're talking about conductive interference, particularly if it's a waveguide, there's common mode signals where the current flows in the same direction on both power lines, and then there's differential mode signals where current flows in this way and back on the other pathway. And depending on the type of interference, you can use capacitors to decouple this. Clearly with the differential mode signals, putting a low impedance across the input and the output of your power supply is one way to avoid that, but they really do have to be a low impedance. And of course, you're probably well aware of this, but electrolytic capacitors resonate at tens of kilohertz, and so above that frequency they look like inductors more than capacitors, and you really have to probably use a range of different capacitors here to make sure that is a low impedance over a wide range of frequencies. For common mode signals, if you're going to use capacitive decoupling, this is the way to do it, and you can also put inductors in the power lines of the different circuits that are connected to a common power path there to avoid interference. This is another slide. This is more like a switching converter, so you can see you've got your input power line. Here's your switch, which is opening and closing. There's a transformer here, and then your output. Common mode interference comes in here and then couples capacitively through to earth. Differential interference just flows in and out on the supply lines. The common mode interference is important, particularly in photovoltaic installations, because the cases of the photovoltaic panels are, if you like, regarded as common in the power system, but they shouldn't necessarily be earthed, or they should be earthed. It's actually also a safety issue, because if you climb up on your ladder and touch the casing on the power converter and it's not properly earthed, then you may get a bit of a jolt from the voltage that occurs between you and ground through that capacitance. Anyway, the ways to deal with this, again, they're mentioned, I think, in that article that Richard gave me about photovoltaics and how to avoid the electromagnetic interference. I mentioned capacitive decoupling on the previous page. Here, an inductor is a good way to avoid common mode interference, so putting a ferrite core around the pair of power lines helps there. And this one is a power filter, so you've got an inductor in each of the power lines, as well as capacitive decoupling across the input and the output. This capacitive decoupling is very important in most power systems anyway, to ensure that they stay stable. Okay, now near-field coupling, how are we going for time? Fine. If you've got two wires running parallel, there will be a capacitance between them, and an electric field or a voltage on one of them can couple to the other through that capacitance. There's a little equivalent circuit. The best way to avoid that is to put a shield around one of the conductors and earth that shield to make sure that the electric fields produced by this wire do not get to the other wire. There are also issues around this with making sure you don't form earth loops and things, which I'm sure you're aware of. So shielding is the best way to avoid electric field coupling. Then if you've got a similar situation with two wires and carrying currents, the magnetic field produced by the current in this wire can link with the circuit produced associated with this other wire and cause a voltage to be induced on that wire. So that's another mode of interference. This is a little equivalent circuit of that situation. The best way to deal with that is to minimise the area of the circuit that you want to avoid interference getting to. So twisted pairs of wires are commonly used in that case, minimises the area of that circuit. And the other way is, again, to use a shield, which instead of having current flowing around this pathway, maybe going back through a casing or a wire that's running a very different pathway back to the supply, the return current goes through the shield very close to the original wire, bringing the power in. And then lastly, Farfield coupling. So when a plane electromagnetic wave impinges on a low impedance surface like a metal, what can happen is that a couple of things. You get a large reflection because of the wave impedance mismatch. You're coming from 300 ohms to a very low impedance usually, if it's a good conductor up at high frequencies. But the wave will penetrate a short distance into the metal, and it attenuates strongly as it propagates through the metal. If the metal is very thin, you'll get some of the wave coming through on the other side. If it's very thin, you may also find that there's some multiple reflection effects that can affect things. But generally speaking, if you've got a good width, a few skin depths worth of metal, you'll get very strong attenuation of a plane wave propagating through a metal shield. And of course, the perfect metal shield, if it's continuous and around the source of interference, none of that interference will ever get out. You've got what we call the Faraday cage. No electric fields generated inside can get out, or vice versa. The sort of shielding effectiveness that you get from a far-field coupling with a metal shield, with reflection, the effectiveness drops off with frequency because the impedance of the metal tends to go up with frequency, but the absorption goes up strongly. So the total shielding effectiveness, this is a megahertz here, starts to go up very strongly after a megahertz. However, you can't have usually continuous metal shields around equipment in practice. You have to let power cables in and out, communication cables in and out, and air in and out or something to cool the equipment. So there's got to be holes in this shield somewhere. And also there's often discontinuities. You know, you'll have a top part of the case and the bottom part of the case, and there'll be a nice U-shaped region where there's not very good contact between the two. That can also be like an antenna which will couple the inside to the outside very effectively. Just to give a quick example of what you'd do in this case, here's your perfect metal shield, and a plane wave impinging on that will induce currents that are uniformly distributed across it. If you put a slot in that shield to let air or anything else through, that forces the currents induced by that plane wave hitting it to go around the slot. That means that you can get a voltage induced from one side of that slot to the other, and there's a principle of duality applies here, but a slot can be just as good a radiator as a piece of wire. So you have to be careful about how you put these holes into the shields, or else you'll be not doing anything with the shield. In this case, it's interesting because you might think, oh, let's make the slot narrower, but that has very little effect on the pathway that the current has to take. So making the slot narrower doesn't really improve the shielding. You'll find that these slots generally have resonant frequencies. You know, it's like a capacitor and then an inductor around the side. So at some frequencies, these things will really radiate strongly, but nevertheless, at any frequency, they are a potential pathway for interference to get through where you think you've shielded. The best thing to do is, instead of having a slot, have a linear array of holes, and then you minimally disturb the currents that would have been there if there were no holes, and you get the best reduction in the you get the best shielding without compromising airflow and things like that. So in conclusion, switch mode power electronics is becoming increasingly common in modern power systems as we move to what we're starting to call an Internet of Energy. You think about packets of energy being shifted around rather than power being provided continuously. This has partly been enabled by advances in semiconductor technology, and particularly widebandgap semiconductors, which are enabling switching frequencies to go higher and the compactness or power density of these converters to reduce. And that's particularly, of course, the case in LED lighting, where you've got the power converter in the back of the light. However, this rapid switching is a cause of electromagnetic interference, which needs to be shielded or and filtered out at the source, or else it causes problems for everyone. The only positive I can see in this for you guys is that as the switching frequencies get higher and higher, maybe the fundamental frequency will be beyond the band that you want to operate in which case you'll be back in clean air again. But if it's a low switching frequency down in the kilohertz range, you'll just have interference the whole way through. And there's not a lot you can do about that apart from try and find the source and do all you can to eliminate it. So there's several potential coupling mechanisms that I've mentioned, common impedance, Nearfield Coupling, Farfield Coupling, and I've tried to indicate a couple of tricks to get around those things, which you can find in many of the amateur radio handbooks, I'm sure. And I've also talked about the standards and compliance issue, and basically it comes back to careful design for electromagnetic compatibility. So if there's any questions, I'll be happy to try and answer them. Yep. Yeah, interesting you should say that. Some people are trying to do that. And in fact, one of my interests is in wireless power transfer, which could be used to charge up electric vehicles, for example, but it could also be used to power implanted medical devices. In fact, the cochlear implant uses just that. They transmit a signal across the skin, and they harvest the power on the inside to power the implant. So there's no physical wiring connecting the outside to the inside world. That's Nearfield Coupling. Farfield Coupling, much less efficient, although I am aware that people are trying to, with arrays of antennas and things, try and concentrate the energy at a point where they can use that to power a passive receiver. Well, the noise is going in all directions and you're harvesting at one point. So what you do in that direction may help people behind you, but it won't help people in any other direction, yeah. Absolutely, it was, yes. There's your original passive receiver. Again, using the emission itself to and converting it down to a lower frequency where the information was contained to power your headphones.
You could get it a lot more popular. A lot of people with new TVs could be taking their TV back to Harvey Norman because the thing turned on or off at random, couldn't they?
That's possible.
And screaming at the 20-year-old behind the counter that this TV turned on and turn it back at.
Yeah. And I imagine that both sides of that equation are as in the dark as each other about what the cause of that is. Could be, causing a lot of waste effectively in perfectly good equipment being returned because someone else is interfering with it unbeknownst. Yeah.
And no party's going to know. All they know is the TV turned on and it's
yeah, which, in those situations is a case for further investigation probably by, I don't know, whom.
Yeah.
To
by who or how much is it for?
yeah.
And the TV that price of the TV costs $1,000.
Yeah. Could be a $5 light bulb interfering with a $1,000 TV.
Yeah.
A greater way might be somebody pacemaker coming.
Yes, well that's where medical devices and things can be designed with electromagnetic compatibility in mind. So it comes down to the designer of the equipment to make their equipment as robust in the presence of electromagnetic interference as possible. And for something like an implanted medical device, that is possible. For something like a radio receiver, you know, you can't isolate it from the rest of the world. You want it to be as sensitive as possible.
So Don would like to hear the story about Morris.
Yeah.
Testing his EMC.
A member of the club who was a pacemaker.
Yeah.
He was a little bit worried about how it's going to work with all these transmitters and things at home. So we went home and we got all the microphones all together, all in one spot. We said to his missus, if anything goes wrong, call an ambulance. He goes, what are you going to do? He goes, watch this. Puts every transmitter on at once.
Yeah.
And we're still standing with phew.
Yeah. So, you know, medical devices are actually tested to a stricter standard, and they probably really are tested. I know Cochlear goes through, you know, hoops that big to make sure their equipment is complies and is safe as possible. It's more the commercial, widely available technology that I think is where the problem is. And yeah. Well, you know, as the pressure to reduce costs goes down, so does the effort going into making these things compatible.
So given that here in Australia that there seems to be little impetus to enforce any standards that may be in existence, is there any other country that does a better job that actually enforces standards?
To be honest, I don't know. It's quite possible that all countries have gone the same way, because the problem is that anyone can buy one of these lights off eBay from China or wherever. There's really no controls over the importation of these things anymore, and until there's a problem, no one knows. Sorry, you, yeah.
How far do you think the noise floor in the suburbs will have to go up before other people are affected?
That's a good question, but I don't know the answer to that. To some extent, it depends on the equipment.
It's going to go up and up and up, isn't it?
It will go up as these power converters become more common. I mean, they're already in your laptops. That's a power converter. Your mobile phone charger has a power converter in it. There's no transformers in these things anymore. They're all switch mode power converters. So they're already quite common, and as they become more common, particularly with solid state lighting, then the problem will get worse. I don't know at what point it becomes an issue. That IEEE Spectrum article that I pointed out says that there already is an issue in some cases, but who's monitoring it, I don't know.
With IT though, I mean, it's question the after 10 years ISM band or different capabilities. So we
Can be, yeah.
saying you're going to interfere that far up?
Well, yes, because, you know, I showed that these devices will produce switching harmonics out to thousands of harmonics. If you're operating at a megahertz, then 1,000 harmonics is at a gigahertz. If you're operating at 10 megahertz, it's at 10 gigahertz. So the higher up in switching frequency you go, the further out the harmonics are being produced. Whether they propagate so far is another question. You know, the higher the frequency you go, the more likely they are to probably get attenuated. But they are still being produced potentially.
Do you think that all the electromagnetic radiation in the air, do you think these people up in arms are worried about the health effects?
Don't tell them. Look, yeah, that's look with power lines, wireless, and all this sort of thing. The tricky thing is finding the physical link between the cause and the effect, and these are probably multifaceted issues. You need this and that and something else to be happening at the same time. So I can't say that it's not an issue, but
No, I'm not suggesting
yeah.
an issue, but I can imagine some fringe groups can get need of it, maybe become a big...
I find global warming doesn't exist, it's just we're getting warmed by the air.
that's another issue, but you know, you're well aware of the concerns around mobile phones, for example, you know, and there you've got a 5-watt transmitter next to your head.
Yeah, but you can catch Pokemons on them, so they only go out the other end.
Well, and my answer is, well, if you don't know, you take all reasonable precautions. And the other thing is there's risks in any technology. You drive down the road, you take a plane, the risks are there. It's a convenience factor, and we will make these trade-offs every day.
I'm not suggesting it's a problem, it's just
No, I know you guys are reasonably, sensible about these things, and it's possible that people might get on a hobby horse about it, but the proof, it's hard to, who knows. But in terms of smart infrastructure being able to operate, yeah, there are concerns, and if traffic lights don't operate properly, or you can imagine all sorts of things happening when you least expect it, could cause actually serious accidents, and that's the sort of thing we should be more concerned about, I think.